What if one of the very first things we learn about physics is just wrong? In this explainer, we're diving into a really provocative theory, one that claims we've all misunderstood something as basic as how water flows. We're talking about a challenge to the very foundations of fluid dynamics. Okay, let's just jump right in. Think about a garden hose. You put your thumb over the end, and the water sprays out faster, right? I mean, that's pretty much physics 101. But what if that's all an illusion? What if the water isn't speeding up at all? This is the core, and honestly kind of mind-bending question we're tackling. So that radical idea is at the very heart of the source material we're looking at. We're going to follow its logic, step by step, using the source itself as our guide, and just see how it builds this completely different picture of how things work. Now, according to the source, this entire theory really hangs on one single foundational law. The claim is, if you accept this one idea, then pretty much everything else we think we know about how fluids move has to change. And here it is. This is the law. It says that inside a fluid, pressure is spread out equally in all directions. You know, think of it like this. In a perfectly still swimming pool, gravity is pulling the same on every single drop of water. It doesn't matter where it is. Well, this theory takes that exact same logic and applies it to moving fluids, treating it as the one single unbreakable rule. And right away, here's the first big consequence of that law. The source argues that if pressure has to be equal everywhere, then there's just no way a fluid can accelerate in a narrow pipe. Why not? Well, for anything to speed up, you need a pressure difference. You need a push from behind, right? This theory says that push simply can't exist because it would violate that fundamental rule. So, if the garden hose isn't speeding the water up, what in the world is going on? How does this theory explain what we see? Well, that brings us to what the source calls the constriction paradox. This slide really lays out the two worldviews perfectly, side by side. On one hand, you've got the common view, fluid accelerates. On the other, you have this theory's claim that the fluid actually jams up. It says the narrowest point doesn't act like a jet engine. It acts like a single toll booth on a 5-lane highway. It ends up controlling the speed of all the traffic stacked up behind it. The source even uses a specific German term for this, staut sich, which basically translates to jamming up or getting congested. And the logic traces right back to that first law. Since the equal pressure can't create that push to force the fluid through any faster, it just has nowhere to go. It piles up, and the entire flow rate of the whole system slows down to match the rate of that one bottleneck. Okay, so how does this whole traffic jam idea play out in the real world? The source gives us a few practical examples to try and illustrate its case. All right, check out this thought experiment from the source. You've got a massive 1-ton tank of water, and it's connected to an empty one by a tiny 1-centimeter tunnel. Now you'd think the immense weight of all that water would create huge pressure and force it through, right? But this theory says nope, that huge tank might as well not even be there. The flow is just going to be a trickle, dictated only by the tiny size of that opening. And this same logic gets applied to machines we use every day. According to the source, things like hydraulic jacks or air pumps don't actually multiply force by using the fluid. I mean, it's a really bold claim. It says any force amplification you get is coming from the mechanical lever you're pushing, not from squeezing the fluid. The theory is super firm on this. If there's no lever, the force stays the same everywhere in the system.
Okay, so if the old rules are out the window, what replaces them? Well, the theory basically throws out complex fluid dynamics equations and proposes a much simpler set of rules for figuring out flow.
And the result is a surprisingly simple model. I mean, forget complicated stuff like Bernoulli's principle. In this framework, flow is just directly proportional to the pipe's size. That's it. So if you've got a pipe that's twice as big, you get twice the flow. And you guessed it, if you cut that pipe size in half, you get half the flow. The bottleneck is literally the only thing that matters. And then we get to what might be the most radical claim of the whole thing. The theory just dismisses another cornerstone of physics, saying that density is totally irrelevant to fluid flow. The source material actually calls it a foreign word, a concept that it claims just doesn't belong in the conversation about how liquids get from one place to another. You know, exploring a theory like this, one that just goes right up against centuries of established science, it really makes you wonder. It kind of forces us to ask, how do we really know which laws of nature are unbreakable? And what does it take for a new idea, no matter how strange it might seem at first, to challenge what we all thought was totally settled science?